Hello everyone and welcome. Today we're going to do a discussion and review over Spanner, Google's globally distributed database. First, let's discuss the topics that we'll be talking about in this presentation. First of all, we're going to do introduction and background because there's a lot of stuff that you need outside information for before going through this paper. We'll discuss some of the problems that Spanner tries to address. Then we'll talk about how Spanner does address those problems. We'll go over some of the data provided in the paper. That way we can compare its productivity, and we'll have a good discussion about whether or not it does or does not address the problems that it seeks to address. And then we'll talk about future work and some of the references so you can look up the information yourself. Okay, introduction and background. First thing you need to know about is a timestamp. A timestamp is something that a computer puts on an event to tell the outside world when that event occurred. For instance, if you're sending a message over like email, that message will have the timestamp in it saying when it was sent. And one thing to note is that in distributed systems, different systems have different clocks that process differently. And that brings us into what's known as clock drift. Clocks inside PCs use crystals that vibrate at very specific frequencies, and the issue is that no two crystals are exactly the same, and since it's counting in microseconds, how fast it ticks time, even what might seem like a very minuscule difference can add up over time, and that's called clock drift, is the difference that two clocks perceive time to have occurred. Alright, and then we'll talk about concurrency. Concurrency is when two processes on different systems occur, and they might have the same timestamp, but we cannot logically prove that one occurred before or after the other one. Synchronization is the effort of a given system to reset all the clocks in the system so that they read the same thing and have them as close as possible. Basically, you want to minimize the difference between the fastest and the slowest system, and you do that by estimating your clock drift and sending messages, which has its own problems, which brings us to latency. Latency is the time it takes to actually send a message from one thing to another. It seems like a lot of things happen instantaneously, but even though the messages are even though messages may be traveling at the speed of light, remember the clock is also vibrating very close to that as well. But everything takes time. So the latency within a certain network might be very big or very small. A message traveling to a computer in the same room will be very instantaneous, while across the country, like sending a message from New York to San Francisco, might take a couple seconds. Replication is something used in distributed systems where a database is mimicked in different spots. And this is to provide more accessibility for users. So you have one database, say on the East Coast, one database on the West Coast, and the idea is that they seem the same. So if a user was accessing them, they wouldn't know the difference. They would assume it's one thing, but it speeds up processes by reducing the latency because you would contact the one that you're closest to. But that also brings in some other issues as to how up to date each one is. If you're talking to one system and someone else is trying to talk to the other one, and you guys are asking similar things, you might get different answers because they haven't synchronized in recent time. Okay, let's go ahead and talk about some of the problems faced with distributed systems, and particularly those relating to databases, as that's what Spanner is specified for. Alright, the first is availability versus reliability. This is one of the biggest things for distributed systems, particularly related to databases. Availability is essentially the user's ability to access the data. So, as we mentioned before with the replicas, the more replicas you have, the easier it is for a given user to access the database. They access a given replica, and it increases the speed, but at the same time you now introduce another problem, which is relating to the reliability. And the reliability is whether or not that data is accurate and how accurate it is up to a given time. So all these replicas have to communicate with each other, because one person in one data center might be editing the database while another person in another data center is trying to read from it. And as they're happening at given times, if the replicas are not up to date, the person reading may have read after the information was updated, but since the replicas haven't updated yet, he'll read old or outdated information. Sometimes they call it stale, especially when referring to timestamps. And the reliability of the network is more or less whether or not that data is good, whether it's up to date. And when all the replicas agree on what the data should be, they call that consensus. And the reliability has to do with whether or not that data is at a consensus, or whether there's discrepancies, whether there's errors or anything like that. And the errors for that can be as simple as the data was not stored properly, or the time sync has gone adrift enough that the timestamps of the reads and the writes are causing the events to happen at the wrong time. And that brings us to the synchronicity of the system. All of these replicas have different clocks because they're different machines in different areas with different crystals. And what they do is they have to pick what they call a time master. The time master is what they call 0, as we addressed. And as the skew or the clock drift reaches a certain level of uncertainty, all these replicas need to query the time master to make sure that they're within a certain range of the clock drift and reset their clock if need be. And what that does is that increases the reliability. The closer they are in sync, the more likely the information is to be correct. And one problem for this is the global distribution. Basically, as you start putting up these data centers with more and more replicas all across the globe, you get more and more latency between transmissions, and significantly different latency as different data centers are much further away. So as you distribute further and further, the margin for error increases because you have to account for how long it takes a message to get from your time master or your replica leader to the other data, to get to the other data centers to update their information, whether it be to synchronize or to change the database. Basically, the bigger it is, the harder it is to manage. All right. One important thing about all databases, though, is platform independence. What this is just does your database work on different architectures? So, say you're using one system in this data center, but over in China you have a different system you're using because the cost of manufacturing varies, and what they build in China is probably significantly cheaper, or you might even just have to use theirs because of other reasons, political, whatever. So what that means is that your system that tries to synchronize all the data in the databases has to work on any machine that they put it on. Ergo, it needs to talk to, it needs to communicate with all of these other systems that may not be the same system, but it needs to communicate as if they were all the same system. And the major thing that comes from this is scalability. Especially when you're talking about global distribution. If your data center can only handle so much and you need another data center, how much more does that add to do? I guess what I'm trying to say is, as far as scalability, the more replicas you add, how much does that increase your latency, or whatever the metric is you're using? You know, how much does that throw off your synchronization? But if something is not properly scalable, in Spanner's case, they used to use MySQL. They developed this spanner because it was not scalable as MySQL. What was happening is the latency was going up much faster than the number of replicas, so it wasn't feasible to have this distributed system on a global scale. Okay, now that we know some of the problems that need to be addressed when we're doing a distributed database, let's talk about how Spanner attempts to address them. First, let's talk about their software stack. Basically, that's just the structure that they use in the database. You know, what software interacts with which other software. And Spanner is pretty typical in this standard. They have what they call a participant leader, which is what the user actually communicates with, and it just has a transaction manager that acts as an intermediary between you and the replica, so that there's not a direct connection between a given user and a replica. And that's more or less for security, but also adds a little bit of the reliability. Okay, and then at the replica, like I said, there's one leader and there's other replicas. You don't necessarily know which one you're talking to, but the replicas do communicate with themselves. They use Paxos, which is a family of protocols that are used for solving consensus in a network where the processors are unreliable. And the unreliability just naturally stems from, like we talked about, the clock drift and the synchronization problem. Reaching a consensus is just part of that. Now within within the replica, there's what they call a tablet and a Colossus. Tablet has the users, the Colossus has all the raw data, and the users have albums, and each album has directories. These directories are given keys that share a common prefix, sort of like buckets. When you do a bucket sort, there's 0, 1, 2, 3, or whatever whatever buckets need to be there. And what that does is that makes the sorting of the data much easier. Okay, and also what Spanner uses is TrueTime. And TrueTime is a set of protocols that they have. They set up a time master, and then they have time slaves, which have a daemon. The daemon is for synchronizations. It is a slowly increasing time uncertainty. And this uncertainty comes from the worst case possible local clock drift. And so what they do is they estimate the worst possible clock drift that they could have, and when this uncertainty from this clock drift reaches a certain point, they make sure they run a synchronization. And we'll talk later in the data section about what they do to keep this lower and how effective it was. Concurrency control is sort of an offshoot of the TrueTime. Basically, the concurrency, not knowing logically whether one event happened before another, reduces the reliability because we cannot guarantee the correctness. So to control the concurrency, they use this TrueTime that keeps a certain amount of synchronization, and it guarantees that a whole database audit read at timestamp t will see exactly the effects of every transaction that has happened as of t. So when they take their slice out of the database, basically if something is said to have occurred before time t, it will show in this slice that it has happened. And their TrueTime is how they deal with that. A major thing that they need for this is good timestamp management. And we'll talk later about their efficiency with their timestamps, but basically they support read-write transactions, read-only transactions, and snapshot reads. And basically those are exactly what they sound. Read-write transactions, either read or write or both. Read-only transactions just get data and collect them. The one difference between the read-write and the read-only that we should say is the read-only pre-declares that it will not have any writes in this transaction. So if there are no writes to the database, it can be called a read-only, and as we'll see later, that's just better performance for the database. It's easier for it to handle. A snapshot read is a read that executes without locking. A client can specify a timestamp for a snapshot or provide an upper bound on the desired timestamp staleness and let Spanner choose a timestamp. Basically, if the timestamp that you send with it is much older than what Spanner's clocks are saying, it will probably give it its own timestamp when it receives it. In either case, the execution of the read proceeds at any replica that is sufficiently up to date. Okay, we'll talk about F1. F1 was Spanner's first experimental trial run. F1 is Google's advertising back end. Basically, when you're on YouTube or whatever, or even when you're searching just on Google, F1 is the database that decides what advertisements you will see when you do that. So you'll run your search, and Spanner will be the database that Google queues with that search. So the keys used would be the words you used in your search. And what happens is it pulls out advertisements that were put into the database to relate to those keywords, and it'll send those back out. So you search for Prada, you get a banner that has Prada purses on it or whatever. You can go shop, or whoever paid to be there probably. All right, and it started out as a MySQL, and the problem with the SQL was the scalability. So what they did was they started to develop this spanner as the F1 was increasing, and they needed better scalability. What Spanner did for F1 is, first, they removed the need to manually reshare, meaning the replicas themselves automatically reshare the information with each other. It doesn't have to be updated manually. Second, it provides synchronous replication and automatic failover. So what that means is Spanner automatically replicates when it sees that it will be more efficient to have another replica. And the failover is when either a replica or the leader has a critical failure and has to restart. Spanner automatically elects a new leader and fills in the missing places. Third, F1 requires strong transactional semantics, which made using other NoSQL systems impractical. And what I think they're trying to say there is that the other databases they were trying to use that might have been scalable were not delivering the ads that needed to be delivered during given searches. So hence the need for their spanner. Okay, let's talk about some of their data. Scalability. The scalability, the latency, as you can see, as the number of participants increase, obviously the latency increases. But as you can see, it is relatively linear with a pretty strong correlation. So what this means is that adding new participants or new data centers, replicas, however you want to say it, adding more only incrementally increases the time needed. So on other ones where it's maybe not linear but it's quadratic or even just exponential, you reach a certain point where the number of participants goes up only slightly, but the latency starts to increase dramatically. And what happens is you reach a cap where, yes, you can handle all of these queries, but no, you're not going to have any because no one wants to use a system that takes forever. We don't go to Google because it is because it's super slow. We go to it because it's fast and reliable. Now let's talk about performance. All right, here's the throughput. And this throughput is just how many actions they can do. And you'll notice that the write is very linear. It's very level. And like I was saying earlier, that this is never going to be very high because you have to update every replica. So the more replicas, the more updates that are necessary. And as you see, as the replicas go up, the processes per second don't go up. It stays pretty level, and that's how they achieve the linear progression. There is by not needing as much. Basically, they're saying no matter how many replicas there are, the throughput for writes is going to be pretty much the same. Now the read-onlys gradually go up, and what that shows is that as the replicas increase, the availability increases. So basically, the more replicas there are, the more throughput they can have, the more read-onlys they can give you. And as you can see, the snapshots go way up because the snapshots are not time dependent. It just changes the timestamp if it looks like it's too old. So all in all, this would be considered a very good performance. It does exactly what you want. You don't lose very much when you're adding the replicas, but you're gaining quite a bit. Okay. Now that we've talked a little bit about what Spanner is, let's talk about whether or not it solves any of the problems that it set out to. Availability. Okay, availability did very well. As the replicas increased, we saw the throughput of the reads and the snapshots go up, while the writes remained stagnant. One problem that they did address is leader crashes. There were 3 different types of tests. There was basically non-leader crash, leader soft crash, and leader hard crash. And what those mean is that a non-leader crash means that a replica that was not the leader is the one that crashed and had to reboot. And this caused almost no problems. They say it had no effect on read throughputs. Killing the leader, but having time for it to hand off the leadership role caused a drop from about 3 to 4%. And that just means that the leader knows it's going to crash, so it does the core dump. You know, if you've ever seen, the blue screen on your Windows machine, that means that it is trying to gracefully exit, but it has to reboot. So the graceful exit for the leader is to pass off the leadership role. And as I said, that they saw around a 3 to 4% drop in throughput there. However, when a hard leader crash means that it doesn't realize that it's crashing, and it basically has a straight drop. They said that the rate of completion dropped to almost 0. So if there's not time for the leader to be reelected, the availability becomes nil. All right, and what they do to try to address this, they talk about the election and recovery. Basically having sort of a pseudo leader, like a vice leader, and that that helps if the leader crashes, the vice leader is, or the pseudo leader is already ready to take over command. And then the recovery. You know, once he reboots and they find out what was wrong, they try and get it back together. Reliability, that sort of leads into what was before. Um, Basically, the synchronizations and the average clock drift. What they were talking about with the daemon, the time slave daemon polls, uh, they have this average uncertainty of what's between the clock drifts, and the time masters, who are not necessarily perfect themselves, but they're the ones that are set to be zero, meaning that whatever their natural drift is from quote unquote real time is what we're gonna say real time is. So uh, what they showed was that basically the average epsilon in the highest percentiles was ranging from like 4 to 10 milliseconds of clock drift, and they were able to reduce it down to sort of a 1 to 5 range. So one way they were able to bring their average uncertainty down was by greatly reducing tail latencies. And what a tail latency is, it's sort of like this outlier on the bell curve. You have a bunch of latencies that are like, 5 milliseconds, 4 milliseconds, right there. But every once in a while, you get this one that's like, you know, upwards of 900, almost a second, almost a full second, which is, ridiculously larger. And reducing these really brings your average way down. So by reducing them, they were able to bring their average uncertainty from between about 2 to 10 down to about 2 to 5, 2 to 6 milliseconds. And, just taking out those big outliers greatly conforms the data and makes it much, much smoother. Okay, F1. As we talked about before, it was the first workload to evaluate Spanner. It works in advertisements. And what it did was it reduced the growth so that they could scale it to a global level, where when they were using MySQL, they just weren't able to scale it the way they would want to. And basically they had to have separate systems in separate areas. Okay, let's move on to future work. All right, one thing they talked about is having parallel reads. So what that basically boils down to is that you can have reads that are, we won't say concurrent, but they're independent. So they can happen at the same time. And what this does is that it allows to queue more from the database and increases the throughput. They also talked about configuring Paxos, and I assume what they mean is that they want to adjust the protocols so that they can be configured specifically for what you're trying to use it for. So instead of having this general protocol that's used for everything, they want to make it so that you can configure your Paxos to work specifically for what you want to work it for, what you're using Spanner for. Another thing they talked about was reducing that clock uncertainty. One thing they did was they worked heavily on the tail latencies. Another thing they're trying to do is they're trying to reduce the time master query, which is just how often the time slaves query the master to bring their drift back down. Another thing they talked about for this is better clock crystals. Um, they they state that they can get better crystals relatively cheap, and all that means is that they're getting close to the same size and structure. The closer they are to each other, the lower the drift should be. And then they talk about better network technology, like how we moved from copper wire to fiber optics, increase the technology. They assume that technology will keep improving, which will naturally reduce latency. The last thing they talked about was improvements on complex queries. One thing we didn't talk about earlier was that a lot of what this is relying on is that uh, there's only a few keys when it's doing its search. So when you do a search on Google, it only uses a couple of the keywords to decide which advertisement to put on the banner. Um, and they said there's relatively poor performance with complex queries. Basically, if you type in the whole title of a published work, like, where it's like it goes all the way past the search bar and you can't even see your whole search at the same time, that greatly reduces the performance of the query because it doesn't really know which keywords are the most important, which advertisement to put up there. So it causes extra latency. Uh, like I said, it was designed for simple keys. And what they're doing right now is they're looking at algorithms and data structures uh, from various areas of database literature to see if they can improve single node performance. And what that means is, like, if they can improve the performance of all the given replicas by improving each one's individual performance. And then lastly, they talked about moving data between centers in response to client load. So if, say, the New York data center is experiencing a lot more traffic than they're used to, or than it normally has, and say there's one in New Jersey, they can send some of those queries to the other replica, the one in New Jersey, and it'll actually have a better latency for everyone because the the throughput on the New York is already pretty much maxed out. But since there's some bandwidth over here, it'll actually be faster for you to not wait in the queue in the New York data center. And with this, they talk about dynamic allocation. Basically, to do that, it has to happen automatically if it's going to save everybody time. If someone has to see that the workload is getting too high and reroute some stuff themselves, then it's not going to save anybody time because then you're working at the speed of human instead of the speed of computer. And like I said, that's part of it. It needs to be coordinated between replicas. You can't just automatically send them over there um, without that replica knowing that the traffic's coming. It has to be automatic but coordinated between the two replicas that are handling the data. Okay, well, that pretty much ends it. Uh, for the references, up here at the top, this is the actual paper. Um, if you look up The Spanner by Corbett James, it'll come up. It's actually a collaboration. There's like 20 different uh, authors listed. He's the first one, so I'm assuming he's the main. And I just looked it up in the ACM database. Uh, for the background information, I used some of the textbooks that were recommended for class. Distributed Systems, Concept and Design. This was, I believe, 5th edition. The most recent as of right now, which is 2018. And then Martin Van Steen's Distributed Systems, 3rd edition, published by Pearson Education. It's the textbook. All right. Thanks for watching. Have a good day.